In this video, we'll discuss factoring. Now, when we think about factoring, we have to first think about the distributive property. With the distributive property, we have some term that is being multiplied to a grouped expression, in this case b plus or minus c. I distribute the a to both terms, so this now becomes the sum or difference of those products. When we're factoring, we're actually going the reverse direction of the distributive property. What we're looking for are common terms or expressions that we can pull out that can then allow us to regroup what is left together. So think about it as taking our equation here and flipping it around. Instead, we start with the AB plus or minus AC and say, okay, both terms in this sum or difference have an A. So I factor that out, and what I'm left with will be grouped together as a new expression. So this would be A times the quantity B plus or minus C. Now normally we start factoring by first looking for monomial factoring within the expression. This means, can we find any common term that can be factored out of all the terms in the expression? This is really the first step we do for any type of factoring. Get rid of the monomial, factor it out to start with. And then we're going to take what's remaining and group it together in a set of parentheses. And then we'll see if we can factor some more after that. So let's look at this expression. 6r to the 4th s cubed t plus 10r to the 5th s squared t to the 4th. So we first look at our coefficients and say, is there a common factor for 6 and 10? And I want the greatest one. So the greatest number that goes into both 6 and 10 is 2. So my common coefficient factor is 2. Now I'm looking at the r to the 4th and r to the 5th. The greatest factor is r to the 4th. With my s's, the greatest factor is s squared. And then with my t's, it's t to the 1st. So I'm going to take my common factors, and that will be my term on the outside of my grouping. So that's 2r to the 4th s squared t. Since I factored that out, I'm going to divide each of my terms by that factor. So 6r to the 4th s cubed t divided by 2r to the 4th s squared t. 6 divided by 2 is 3. R to the 4th divided by r to the 4th is 1. S cubed divided by s squared is s, and t divided by t is 1. So all that's left is 3s. I do the same thing with my second term. 10 divided by 2 is 5. R to the 5th divided by r to the 4th is r. S squared divided by s squared is 1. And t to the 4th divided by t is t cubed. So that's plus 5rt cubed. And there's nothing else I can do to factor this expression. So this would be the factored form. Now we can then say, okay, after we've done our monomial grouping, can we factor by other grouping? So what do I mean? Let's look at this 4-term expression. The first thing I do, and it's not required, but I find it to be very helpful, is to convert all of my subtractions to plus and negative. Remember, a polynomial is the sum of expressions. So I change those to plus and negative to make it easier to deal with. So instead of minus 8xy to the 4th, that's plus and negative. Instead of minus 4y to the 4th, that's plus and negative. Now that grouping piece, I'm going to group terms together. And when there's 4 like this, I group the first 2 together and I group the second 2 together. And I leave that sum that's in between those two sets because these are all sums. It's the associative property of addition if you really want to get to the technical terminology of what's occurring here. Now that I have separate groupings, I can perform monomial factoring on each grouping and see what comes out. So that's what I'm going to do here. If I look at 6x squared plus 3x, I can factor out a 3x from both terms, which will leave me with 2x plus 1. If I look at my second grouping, I can factor out this negative 4y to the 4th, and that will leave me with 2x plus 1 again. And that's a key part here. what I want to see is that when I get the grouping, that there is a common expression left inside the factors. If not, I'm done. I can't do anything. But in this case, I do have a common grouping, which is the 2x plus 1. So my final thing I do is I'm going to group the factored terms together and multiply that by that common expression. So my factored terms are 3x plus negative 4y to the fourth, and then the common is 2x plus 1. Now you probably notice right here, I didn't write this as plus and negative, I converted it back to minus, because often your final solutions will use the operation of minus versus writing plus and negative. Both are accurate, but the most common way you'll see it is a minus. Now we can also use this if we're looking at trinomials. That's a 3-term expression. These are some of the most common you see within algebra courses. So say that we have something like x squared plus x minus 12. The first thing we look at is the product of our highest degrees coefficient by the constant. In this case, that would be 1 times negative 12, which is negative 12. Using this product, we're going to create factors of that product that will sum to our middle term. So we have here the product is negative 12, so we're looking at its factors. Since the middle term is positive, we know that the greater factor should be positive as well. So let's look and say, okay, negative 1 and 12, those are two factors, but negative 1 plus 12 is 11. Nope. How about negative 2 and 6? Well, negative 2 plus 6 is 4. That isn't it either. Well, the next one would be negative 3 and 4. Well, negative 3 plus 4 is a positive 1. And this is a positive 1 coefficient, so that's what we need. Now what we're going to do is replace that middle term with our two factors. So in this case, instead of having plus x, we could rewrite that as minus 3x, or plus and negative 3x, and plus 4x. And here I change this to plus negative 12. Again, taking the negative and making it plus, or taking the subtraction and making it plus negative. So negative 3x plus 4x is still 1x. So I haven't changed the actual value of the expression. It's just now I can work with it to factor. Because once I have 4 terms, I can group factor just like I did a minute ago. So I'm going to group my first 2 terms and group my second 2 terms. When I look at x squared and negative 3x, I can factor out an x, which will leave me with x plus negative 3. In my second one, I can factor out a 4, which will leave me again with x plus negative 3. I have that common term, so I know that this can be factored. So I'm going to take my 2 factors and group them, and then I take my common factor and make that the second grouping. So this is x plus 4, and then x minus 3. Again, instead of plus and negative, I just change that back to minus. Now what happens though if I have a coefficient on the x squared like this? It's still the same process. So first thing, 8 times negative 5 is negative 40. So now let's look at those factors and see which ones would sum to negative 18. Since this is negative, I know that my greater factor should be negative as well. So 1 times negative, or 1 plus negative 40 is negative 39. Nope, too big. What about 2 plus negative 20? Well, that is negative 18, so there I found it. So now I can replace that negative 18x with plus 2x plus negative 20x. And again, if I combine them, it is the same value. But now I can group. So I'm going to group my first 2 terms, group my second 2 terms. Say, okay, what can I factor out of this? I can factor a 2x. What can I factor out of this? I can factor out a negative 5. That leaves in both terms 4x plus 1. So I again have a common factor. I'm going to group my 2 factors together and then write my common factor. So in this case, 2x minus 5 times the grouping quantity 4x plus 1. Now let's look at a couple other things that can happen. One of those is the difference of perfect squares. Now, first understand, if you're missing that middle term of a trinomial, you could put the plus 0x there and then use the steps we just did. But this is one that can be very helpful to recognize it as a quick way to do a factor. If I recognize that both terms are perfect squares and it is a difference, only if it's a difference, I can write that as the quantity a plus b times the quantity a minus b. So those are the square roots of those two terms. Let's look at an example here. 9x squared minus 49. So yes, I could put plus 0x in the middle and then work through the trinomial steps I just did. Or I can recognize that these are perfect squares. If I take the 9x squared, the square root of that would be 3x. So my a value is 3x. If I take the square root of 49, that would be 7. So my b value will be 7. That means that if I think about my difference of perfect squares, I could rewrite this with my a being 3x, my b being 7, as the quantity 3x plus 7 times the quantity 3x minus 7. Now, one last thing that can happen is what happens when I have other degrees that are greater than 2. Think about that first monomial expression we had. There were degrees all over the place. What's the first thing we did? We factored out any term we could. So again, we always start by factoring out everything possible from that monomial type of expression. Then we look at our grouping that's left and say, can we do trinomial factoring? Can we group factor? Is there a difference of perfect squares? And once we factored that, we look at each of those individual expressions and say, can I continue to factor it all? And we keep going until we're done factoring. So let's look at this expression here. X to the fifth minus 256x. First, start with the monomial factoring. They both have an x. I'm going to factor out x. That gives me x times the quantity x to the fourth minus 256. Now I'll look and say, okay, there's only two terms there. Let's see if it's a difference of perfect squares. And x to the fourth, I can take the square root of that. X to 256, yeah, it's 16. So I can do a difference of perfect squares. So I can think about the square root of that would be x squared for my a value. My b value would be 16. So I can rewrite that then as x times the quantity x squared minus 16 times the quantity x squared plus 16. Now I have to ask myself again, can any more of these factoring methods be done with either of these two terms? Well, I need to look at that middle term. That middle expression there is x squared minus 16. That again is a difference of perfect squares. So I'm going to take that term right there and I'm going to use that again. The square root of x squared is x. The square root of 16 is 4. That means I can split that into x times the quantity x minus 4 times the quantity x plus 4 times the quantity x squared plus 16. And then I'm done. Now you may ask, why not the second x squared plus 16? That is a sum. I cannot do it to a sum, only to the difference.